In the previous few classes, we were discussing about covariant differentiation. That is, the covariant differentiation of a covariant tensor is given by covariant differentiation of a covariant tensor is given by partial derivative of a nu with respect to sigma, Christoffel symbol rho mu sigma a rho. Now, to perform the second derivative, I have to once again apply the covariant differentiation to the above expression. Okay, so this is known as successive covariant differentiation. To perform the second derivative, I have to once again apply covariant differentiation. Okay, so this is known as successive covariant differentiation. So here I have taken the covariant differentiation with respect to sigma, right? So next I take the covariant differentiation with respect to lambda, okay, of this quantity. Covariant differentiation with respect to sigma a nu. Then I have to take the covariant derivative on the right hand side also of a nu with respect to x sigma minus Christoffel symbol rho nu sigma a rho. Okay, so I am taking the second derivative of this quantity. Okay, that is with respect to lambda. Now I have to simplify this. So first I have to apply the covariant derivative to the first term and then to the second term. Okay, so first I apply to the first term. Then I will get I am applying this to a nu. Okay, a nu minus, now I have to apply to the second term. Second term actually has a multiplication. So first I will write the Christoffel symbol as it is. Okay, then apply the covariant differentiation to a rho. Then I will apply the covariant differentiation to the Christoffel symbol and I will keep a rho as it is. But we know that Christoffel symbol contains g mu nu and covariant derivative of the metric tensor is 0. Therefore, this entire term will go to 0. Then, so here you have only two terms, right? I can write. Now I have to expand this term, the covariant derivative of a nu with respect to lambda. That will be partial derivative of a nu with respect to x lambda minus Christoffel symbol mu nu lambda a mu. Then minus Christoffel symbol. Now again I have to expand this term. That will be partial derivative of a rho with respect to x lambda minus Christoffel symbol mu rho lambda a mu. Okay, and the last term will go to 0. Hence, I have taken the covariant derivative with respect to sigma first, and then covariant derivative with respect to lambda, right? First I have taken with respect to sigma, then with respect to lambda. So 2 times I have taken covariant differentiation, which means this is successive covariant differentiation. So let this be equation number 1. Now next what I am going to do is that first I will take with lambda, then with the sigma, okay, of the same quantity A nu. So next I am going to do this. First with respect to lambda, then with respect to sigma. Okay. So let this be equation number 1, and I am going to write covariant differentiation of A nu. So this will be equal to covariant differentiation of, now I have to write this one, expand this one, right? That will be A nu with respect to x lambda minus rho nu lambda A rho. Now again I have to do for both these, right? So in the similar way I write partial derivative of x lambda covariant differentiation of A nu minus Christoffel symbol as it is covariant differentiation of A rho, then covariant differentiation of Christoffel symbol A rho. So similarly here also this term will go to 0. Then I can write, I have to expand the covariant differentiation. That will be partial derivative with respect to x sigma A nu minus Christoffel symbol rho nu lambda A rho minus Christoffel symbol rho nu lambda. Again I have to open. So partial derivative of A rho with respect to x sigma minus mu rho sigma A mu. Let this be equation number 2. Okay. Now what I am going to do is that I am going to subtract equation 2 from equation 1. Okay. If I subtract equation 2 from equation 1, on the left hand side I will get A nu minus sigma lambda A nu, right? But if you watch it or observe it more closely, you can see that, if you observe more clearly, you can see that this is nothing but the commutator of the covariant differentiation of with respect to lambda and with respect to sigma, then A nu. So this is the commutator, right? Now I have to subtract on the right hand side also. Okay, so equation number 1, this is the right hand side, and equation number 2, this is the right hand side. So the commutator bracket of covariant differentiation with respect to lambda and covariant differentiation with respect to sigma of A nu is equal to second derivative of A nu minus A mu. I'm just doing this right hand side, okay, this one. I'm opening and then subtracting. So here there is a second derivative. Similarly, here also there is a second derivative. I'm opening up all the brackets and then subtracting the right hand side. Minus mu nu lambda partial derivative with respect to x sigma of a mu, then minus rho nu sigma a rho with respect to x lambda plus Christoffel symbol rho nu sigma mu rho lambda a mu. This is the first equation number 1. Okay, now I am going to write equation number 2 minus, this will be equation number 2 with respect to x lambda x sigma minus a mu minus rho nu lambda plus okay, so this is equation number 2. This is equation number 1 up to this, then subtracted by equation number 2. Okay, now we have to cancel what all terms are there that will cancel, we'll check. So you can clearly see that this will cancel, right? This term will cancel, then this term will cancel with this one. Okay, that will cancel. Then this term will cancel. Yeah, I think that's it. So all these terms will cancel. Then I can write the remaining terms. The remaining terms will be x lambda mu nu sigma a mu minus a mu plus rho nu sigma mu rho lambda a mu minus Christoffel symbol rho nu lambda, Christoffel symbol mu rho sigma a mu. So in all these terms we have a mu common. So if I take a mu common, then I will get mu nu sigma with respect to x lambda, then minus mu nu lambda with respect to x sigma, then nu sigma mu rho lambda minus rho nu lambda mu rho sigma. So So you get A mu multiplied by a very big quantity, right? So let's define the quantity in this bracket as the Riemann curvature tensor. So this is the Riemann curvature tensor, R mu nu lambda sigma. Okay, so this entire quantity will be equal to A mu R mu nu lambda sigma. Okay, so I define the Riemann curvature tensor R mu nu lambda sigma is equal to partial derivative of mu sigma with respect to x lambda minus partial derivative of mu nu lambda with respect to x sigma plus Christoffel symbol rho nu sigma, Christoffel symbol mu rho lambda minus Christoffel symbol rho nu lambda multiplied by Christoffel symbol mu rho sigma. So this is known as the Riemann curvature tensor. Okay, so I have defined the Riemann curvature tensor from the commutator bracket of the two covariant differentiation. So I'll write it once again. The commutative bracket is equal to A mu R mu nu lambda sigma. Here R mu nu lambda sigma is the Riemann curvature tensor. The Riemann curvature tensor is a mathematical tool, okay, that is used to quantify the curvature of the Riemannian manifold. And R mu nu lambda sigma is a mixed tensor of rank 4. Okay, it describes how the geometry of a space changes at different points because it measures the non-commutativity of second derivative of the vector field. If it commutes with each other, these two commutes with each other, then it will be 0. Okay, so Riemannian curvature tensor measures the non-commutativity of the second derivative of the vector fields. So this is the way it captures the curvature. For example, you have given a manifold, then how do you know whether it is curved or it is flat? It's very difficult to say from the metric because, for example, in special theory of relativity, the metric is given by ds square is equal to c square dt square, right, minus dx square plus dy square plus dz square. So this can be written as eta mu nu, right? So I have to write summation over mu comma nu from 0 to 3 eta mu nu dx nu dx nu, right? So here eta mu nu is the fundamental metric tensor in the Minkowski space. Because we are using the special theory of relativity, it will be a Minkowski space, right? So eta mu nu will be the fundamental metric tensor in Minkowski space, and it is given by, you can see from this equation, it will be, so suppose c equal to 1, then it will be 1 minus 1, right, minus 1 and minus 1. All the other will go to 0, right? So this is in special theory of relativity. Okay, the elements of the Minkowski metric are constant and they are not coordinate dependent. You can see they are 1, -1, -1 and -1. So they are not coordinate dependent. But the moment you include gravity, it gets complicated. So in here in special theory of relativity, gravity is not included. Okay, so the moment you take general theory of relativity, gravity is included. Okay, the moment you include gravity, it gets complicated. So the new form including the gravity will be ds square is equal to summation over mu nu from 0 to 3 g mu nu of x mu dx mu dx mu. Okay, so here gravity is included. Where it is included? Here, because the fundamental metric tensor is now a function of the coordinate. So when you try to describe gravity, the corresponding geometry would be non-Euclidean. Or Riemannian. Okay, so the moment you include gravity, the fundamental metric tensor will be a function of coordinate, and when you try to describe gravity, the geometry would be non-Euclidean or Riemannian. But there are a lot of confusion among this. Okay, for example, if you take this, if you consider a sphere of radius a, okay, consider a sphere of radius a which is embedded in a Cartesian coordinate system. Okay, for example, consider a sphere which is embedded in a Cartesian coordinate. Okay, so this will be x, y, and z. Then you can write the equation of this sphere as x square plus y square plus z square is equal to a square, right? Similarly, here I can write ds square as dx square plus dy square plus dz square. If I do some coordinate transformation, for example, from this xyz to r theta phi, okay, from Cartesian to spherical coordinate, that is xyz to r theta phi, then x will be r sin theta cos phi, y will be r sin theta sin phi, and z will be r cos theta. Now if you try to describe ds square, then it will be dr square plus r square d theta square plus sin square theta d phi square. But if you write the fundamental metric tensor from here, then you will get 1, 1 and 1, right? But if you take the fundamental metric tensor from here, then you will get 1 r square and r square sin square theta. So here there will be a confusion. People think that this is flat space and this is curved space-time, but actually not. Both are flat. Okay, so this dependence of metric tensor on the coordinate is actually a coordinate artifact. This is just a coordinate artifact. Okay, it is still in a flat space. It's not curved space. We have just transformed from Cartesian coordinate to spherical coordinate system. That's it. So from merely looking at the metric, you cannot say whether the given space is a flat space or a Euclidean space. For that, you have to compute the Riemann tensor. So that is the importance of the Riemannian tensor R mu nu lambda sigma. Okay, so R mu nu lambda sigma is a mixed tensor of rank 4, and that describes how the geometry of a space changes at different points. It measures the non-commutativity of the second derivative of the vector field, and that is how it captures the curvature. So how do you know that the given space is curved? Okay, so it measures the non-commutativity of the parallel transport of vectors. The moment you take the covariant differentiation, it is dependent upon the parallel transport of a vector. So when you take the commutator, then it says that the vector has changed, because the commutator is not equal to 0. It has some quantity, it has some curvature, which means that if you the vector has changed, and the parallel transport, when you this is nothing but the subtraction of two parallel transport, and that is not equal to 0, that is equal to some curvature, which means that if the parallel transport is not commutative, it means that the vector has changed and the space is curved. The vector will change when you parallelly transport it from one point to another point in a curved space only, right? Therefore, if the parallel transport is not commutative, it means that the vector has changed and the space is curved. Therefore, it captures the intrinsic curvature of the manifold. Okay, so unlike this is not the intrinsic curvature. This is actually arising due to the coordinate artifact. So Riemann tensor helps us to check whether the given manifold is flat or curved. Okay, therefore Riemannian curvature tensor plays a crucial role in Einstein's theory of general relativity, and the Ricci tensor can be obtained by contracting the Riemann tensor with the metric tensor. So once you get this Riemann tensor, you can obtain Ricci tensor by contracting the Riemannian tensor. And once you get the Ricci tensor, you can get the Ricci scalar or the scalar curvature by contracting the Ricci tensor. Okay, now we see the properties of Riemannian tensor. So the Riemann tensor is anti-symmetric with respect to the last two indices. So we'll check. First, I'll write the definition of the Riemann tensor. R mu nu lambda sigma is equal to partial derivative of Christoffel symbol mu nu sigma with respect to x lambda minus partial derivative of Christoffel symbol mu nu lambda with respect to x sigma plus Christoffel symbol of rho nu sigma mu rho lambda minus rho nu lambda Christoffel symbol mu rho sigma. Okay, now we have to check with respect to last two indices, that is lambda and sigma. I have to interchange. I'll interchange lambda and sigma and check whether Riemann tensor is anti-symmetric with respect to the last two indices or not. So after interchanging, I'll get R mu nu. Now instead of lambda, there will be sigma, then lambda. So this is equal to, now wherever there is lambda, I have to substitute with sigma, and sigma I have to interchange with lambda. Mu nu, now instead of sigma, I have to write lambda. With respect to, instead of lambda, I have to write sigma minus partial derivative of mu nu sigma with respect to x lambda plus Christoffel symbol rho nu lambda mu rho sigma minus rho nu sigma mu rho lambda. I will take negative outside and check, because I have to check whether this is anti-symmetric or not. So I'll take out a negative and see. So once I take the negative outside, then I'll get mu nu sigma with respect to x lambda, this term. So negative is outside. Now I have to write this term, but I have to put a negative. Mu nu lambda plus, now I'll write this term, okay, negative is there outside, so I can just write Christoffel symbol rho nu sigma mu rho lambda. Now finally this one I have to write a negative Christoffel symbol rho nu lambda, Christoffel symbol mu rho sigma. But if you compare this bracket with our original Riemann tensor, then you get this is equal to minus r mu nu lambda sigma, okay, which means r mu nu sigma lambda is equal to negative of r mu nu lambda sigma. Okay, therefore the Riemann tensor is anti-symmetric with respect to last two indices. So if you interchange the last two indices, then you will get Riemann tensor is anti-symmetric. So in 4 dimension, r mu nu lambda sigma has 256 components. But after applying the anti-symmetric property, then r mu nu lambda sigma has only 20 independent components. So all other components you can get by exchanging lambda and sigma. So these are only 20 independent components are there. Okay, so that is coming from the anti-symmetric property. Now by definition I can write r mu nu lambda sigma as partial derivative of mu nu sigma with respect to x lambda minus partial derivative of mu lambda nu with respect to x sigma plus Christoffel symbol rho nu sigma mu rho lambda minus rho lambda nu mu rho sigma. Okay, so this is the Riemann tensor. Now I am going to do cyclic permutation of the covariant indices. Okay, so r mu I am keeping as it is. I have nu lambda and sigma. So sigma will go to nu will go to lambda, lambda will go to sigma. I'm going to do the cyclic permutation of the covariant indices. Okay, then R mu will be as it is. Now I'll get sigma nu lambda. So first cyclic permutation, I'm just taking this sigma to the other side. Okay, that is, I'm exchanging sigma with nu. This operation I'm going to do sigma with nu, and therefore it will become partial derivative of mu sigma lambda minus partial derivative of Christoffel symbol mu nu sigma with respect to x lambda plus Christoffel symbol rho sigma lambda mu rho nu minus mu nu sigma mu rho lambda. Okay, now I do one more cyclic permutation. Okay, so this time lambda will come to sigma, so I interchange lambda and sigma. So one more cyclic permutation, then I will get R mu lambda sigma nu is equal to, so wherever there is sigma I am replacing it with lambda, wherever there is lambda I am replacing it with sigma, which is equal to mu lambda nu x sigma mu sigma lambda x nu plus mu rho sigma minus mu rho nu. So I have three equations. So let the first one be equation number 1, and let this be equation number 2, and let this be equation number 3. Now I add 1 plus 2 plus 3. Then I'll get on the left hand side R mu nu lambda sigma plus R mu sigma nu lambda plus R mu lambda sigma nu is equal to, now on the right hand side, see this term and this term will get cancelled because here there is a negative, and this term and this term will get cancelled. Similarly, this term and this term will get cancelled. This term and this term will get cancelled. Then nu sigma lambda and sigma lambda, this will get cancelled, and this one and this one will get cancelled. So I'll get this is equal to 0. This is an important result. Okay, so if you take the Riemann tensor and cyclic permutation, if you do 2 cyclic permutations and add all of them, you will get the result equal to 0. Similarly, the sum of the covariant derivatives of this quantity will also be 0. That is, covariant derivative of plus is equal to 0. Okay, so these are very important results and these are known as the Bianchi identities. Okay, one is algebraic identity. This is Bianchi algebraic identity, and the second one is Bianchi differential identity. So these two are very important results known as Bianchi identities. Okay, so for today we'll stop here.